Alright, the second problem we're going to solve here is a little more involved. In this problem, you have some kind of chemical reaction that is releasing a certain amount of energy. So this amount of energy is being released, and therefore this type of energy is going down as part of its release. You're also told that this energy is converted into new chemical bonds with a particular efficiency. And given these pieces of information, what you're actually has to find is how much temperature change will you get in the water, given that you have its mass and its heat capacity. So we talked a little bit about the lecture about how to deal with heat or thermal types of energy. The change in thermal energy for your system can always be found by taking the mass of your system, multiplying it by your heat capacity, and multiplying it by the change in your temperature. Now, the question is, how do you go about solving this? And the answer is to use the exact same energy conservation tools that we've been using previously. We're just going to be adding heat as a new type of energy. So to start this off, what I would recommend you do is organize your information that you're provided with so that you can most effectively solve a problem in this fashion. So because we're going to be using energy to deal with this type of problem, we're going to want to figure out what types of energy we have. We're going to want to figure out initials and finals where they're relevant. And we're going to do all of that so that we can find the changes in energy and ensure that if we keep track of everything, we know everything about our system, all those changes add to zero. Now, if you take a look at this particular problem, there are a couple things here uh, that you need to deal with because there's actually several types of energy present here. First of all, you're told that there's an energy associated with the chemical reaction. Uh, you're actually told that in the very first sentence of this problem. Secondly, you're told that there is a type of energy associated with chemical bonds, or the bonds between atoms and molecules. That's actually what's underlined in orange up here at the top. And then lastly, there is an energy associated with thermal energy or temperature. And for thermal energy, we have an equation for it. Right, so you have to be able to deal with all of these three. Now, in order to do this, what you're going to want to do is you're going to want to break your problem down at the start. Very first thing you're told is that the chemical reaction is releasing energy. In other words, if we're viewing this reaction as something that stores energy, first of all, we're not being told how much of it we have. We're simply being told how much it changed. And because it is releasing energy, the energy stored in the chemical reaction itself is going to go down by 240 joules. Right? That 240 joules is going to be used elsewhere. And that's the very first one we can fill out. We can then work our way around this chart. Now, the second thing that we're told is our energy is being converted into the formation of new bonds. So just like with the chemical reaction, we aren't told how many bonds we start with or end up with. So all of our math is just going to be dealing with the change. And lastly, if you take a look at our thermal energy equation, it is a delta equation. So likewise, we don't have to worry about initial and final for that. So for this problem, in terms of dealing with energy, we're only going to be looking at the changes. So what I'm going to do here, just for the sake of simplicity, is since we do not need initial and final for this particular problem, because all we're dealing with is types of energy that are gaining or losing energy, we can just deal with the changes and make sure they add up to zero. Now, with that being said, we need to fill in the rest of this. You are provided here with an efficiency. Anytime you're provided with an efficiency, what it's doing is it's converting out, or it's comparing output to input. Right? So it's literally a division of output over input. Now, in this particular case, you actually, for your efficiency, you need to look at what it is actually with respect to. So what it's saying is that chemical energy, or that energy, is converted to the formation of new bonds. So the output for this efficiency that you've been provided with is comparing bonds to the reaction. Right? You have to, whenever you're dealing with efficiencies, you got to be told what you're converting between. Now, with this being said, we do know that our efficiency is 34%, or 0.34. Always use the decimal when you're dealing with math. Our output, don't know what it is, so let's just leave it as a variable x. And this is divided by the input energy that is being used to create this energy. So our chemical reaction is giving up 240 joules, so therefore our input is 240 joules. Now, if you put this in, what you will actually receive when you solve this, you're going to rearrange it and solve it for x, so we can just get rid of this equal sign and move down to the next line. If you rearrange this and solve this, what you will get is x is equal to, let me just math this, 81.6. What this basically tells you is that the bond energy is picking up 81.6 joules. Now, with those two out of the way, we are told what the change in the chemical reaction energy is. We can use our efficiency to figure out how much energy is being gained by the chemical bonds. Our very last step would be to find out, based on our energies, how much our thermal energy has changed. Now, you can do this because at the end of the day, we have identified all the types of energy that are present. All we need to do is ensure that this change column adds up to 0. So if you go down this chart here, you can say right away that the change in thermal energy, let's make it red here, is 158.4. Now, once you've identified this, again, we'll just slide this over. Your goal is to figure out how much the temperature of the water will increase. So just like before, once you filled in all of your energy changes and all of your energy types, one of them will actually help you solve the problem. Since we're looking for changes in temperature, we should probably be using changes in thermal energy. So we can use this change in thermal energy directly to find our change in temperature, because our change in thermal energy, delta E thermal, is equal to our mass times our heat capacity times our change in temperature. Now here we know that delta E thermal is 158.4. Here we're provided with the mass. Now the mass is in grams. All right, it's provided to you in grams, but so is the heat capacity. So these will cancel out and we can just use the numbers. So here our mass is in grams and it is 100 grams. And our heat capacity is also in grams, 4.184. Now, once you have this, you can rearrange and solve for delta T. Now, if you do so, what you will find is delta T will be equal to 0.379 Kelvin. Now, the very last thing I will mention is we know this temperature is in Kelvin because our heat capacity is also in Kelvin. So the units will match up with whatever you're doing. And with that, we can find the change in temperature of our system.